Good day all of you. In this class, I want to explain relationship between power spectral density PSD of output and the power spectral density of input of an LTI system with random input process. Okay. So now consider an LTI system . Yes, consider this as your LTI system. Consider x of t as the input random process and y of t as the output random process. Okay. Then if this random process x of t, input random process x of t, assume it to have the PSD as xx of omega and this PSD as syy of omega. The relation between sxx of omega and syy of omega is syy of omega is equal to mod h of omega whole square into sxx of omega. What is this h of omega? H of omega is nothing but transfer function of your LTI system. Okay. So this is the relation. Okay. Now we'll prove it. Yes. We know the output power spectral density is syy of omega is the Fourier transform of autocorrelation function of the output response Ryy of tau. Okay, that is Fourier transform integral minus infinity to infinite Ryy of tau into e power minus j omega tau d tau. And we already derived the autocorrelation function of the output process y of t as Ryy of tau is equal to integral minus infinity to infinite Rxx of tau plus delta 1 minus delta 2 h of delta 1 h of delta 2 d delta 1 and d delta 2. This is the autocorrelation function of the output process y of t. Now substitute this Ryy of t in this expression. It implies yy of omega is equal to just substitute here integral minus infinity to infinite. In the place of Ryy of tau substitute. Okay, and the remaining is e power minus j omega tau d tau. So now if you separate this total as like integral minus infinity to infinite, you just take the first one h of delta 1 and the second one h of delta 2 and for the third integration you take integral minus infinity to infinite Rxx of tau plus delta 1 minus delta 2 e power minus j omega tau d tau d delta 1 and d delta 2. Okay. Now let delta as tau plus delta 1 minus delta 2. I'll get d delta as d tau, and you can write tau as delta minus delta 1 plus delta 2. Substitute all these things in this above expression. Yes, I'll get syy of omega as, yes, first one. Yes, if you substitute tau is equal to delta minus delta 1 plus delta 2, just substitute here. Okay, and if you separate delta minus delta 1 delta 2, then see here, integral minus infinity to infinite h of delta 1. Then here in this tau you have these three terms. So in these three terms you separate this minus delta 1 and you take that minus delta 1 term for this one. Okay, so it is e power, yes, e power j omega tau 1. Okay, yes, if you substitute this, it is e power minus j omega delta and minus plus, so e power j omega delta 1 and minus e power j omega delta 2. So it is integral minus infinity to infinite h of delta 1 into e power j omega delta 1 d delta 1 plus integral minus infinity to infinite h of delta 2 e power, so again for this delta 2 you will get minus, so it is e power minus j omega delta 2 d delta 2. Integration, integral minus infinity to infinite. Yes, it is for this place, yes, we already consider it as delta. So rxx of delta into, yes, as these terms, these two terms are over for h of delta 1, h of delta 2 will be with only delta. So it is e power minus j omega delta d delta. Okay, so now if we see the second term, it is like the Fourier transform h of omega, integral minus infinity to infinite h of delta 2 into e power minus j omega delta 2 d2. So it is like h of omega. So now if you observe the first term, as here the sign is positive, so it will be h star of omega, h star of omega, okay, yes, into, now if you observe this last term, it is nothing but your s xx of omega. Yes, the Fourier transform of autocorrelation function of the input is nothing but your input power spectral density. So now if you observe totally, yes, yy of omega, yes, this is the multiplication of h of omega and its conjugate is nothing but your h of omega whole square and yes, xx of omega. Okay, so this is the relation between power spectral density of output and power spectral density of input.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.